My talk was entitled Who Moved the Goalposts? It was a discussion on the rapidly evolving state of PC architecture, dealing with the topic that over the last 3 to 4 years Intel has introduced a tick-tock model where we change architectures every 2 years, and on the alternate years we're actually updating the architecture, the process. So we've moved from 65 nanometers, 45, we're moving to 32 nanometers very shortly. This has a big implication for someone writing a game. Usually the game takes several years to develop, and the game, when it comes out, has to support hardware that probably dates back 3 to 4 years. And depending on the type of game, they might want that to be running for maybe a couple more years, especially if it's something like an MMO that has a very long lifespan. If you're memory bound, you can double the number of threads, and you still have more bandwidth per thread than you used to have. So that's going to help you quite a lot. So, when writing their game, they need to make sure that the code actually runs well and makes the best use of a whole variety of hardware. It needs to adapt, basically. And this slide isn't really here just to actually list them. It's to give you an overview of where SSE and when it was introduced. There's a couple of interesting points. SSE2 was actually introduced in 2000. So just about any game being written today is only going to be running on something with SSE2 or above. The current generation of CPUs offers several big advantages to games developers. They come in several different areas. We have the advancements in multi-threading. We've moved from single threads to dual, quad, and we're now up to running 8 logical processors on a single desktop CPU. That makes for a huge difference in the amount of code that can be executed on a frame-by-frame basis. But it's not the only thing we've done with CPUs. We've also introduced new architectural improvements. The Core i7 offers significantly higher memory bandwidth. It's much faster at accessing the memory. There's been improvements in terms of how fast it can execute instructions. The branch misprediction is better. It's improved the store load. This means even generic code will behave faster than on previous generations. And it's up to games developers to find things that make use of that. It gives them the ability to add more to their game while maintaining the same frame rate. And then that will tell you how you can enumerate your cores. Once you've done all of that, you still need to go and actually write a piece of code that actually calls CPU ID on multiple thread, actually binds threads, calls the CPU ID, gets the information back from the processor you're running on, and builds that into a small table that you can then actually figure out what cores are shared with what other cores, how the caches are linked up. Very complex code. If you run a game and find you're using thread affinity to make it work, to make things behave, there's probably a bug in the code. You should always be able to run your code with no thread affinity set whatsoever. Thread affinity is only something that potentially gives you a slight performance improvement. There are several things that game developers need to be aware of and things they can do to make the best use of hardware. The first thing I'd ask any game developer designing a new game to do is build in from the day one a way to profile and test their application. They want to know, as people on their team are improving and adding new features, that there is an easy way they can test that on a variety of different pieces of hardware. The game will behave differently if you're on a Pentium 4, Core 2 Duo or a Core i7. The original Pentium D, where you had 2 cores communicating across the front side bus. The Core 2 Duo, which effectively has a dual core sharing a level 2 cache. Then on a quad core system, 2 of them communicating across the front side bus. And the Core i7, where all the cores, whether it's 2, 4 or 8, are sharing a shared level 3 cache. Very different behaviour. If you've built something in from day one that allows you to test that, you're going to be in a much better position than if you actually leave that till the end of your game design period. The other thing they can do is make use of the best tools available. And there's a whole range of tools. They range from profiling tools, some of which are free. You have everything from VTune, Thread Profiler, we have graphics profiling tools, we have plugins for Dev Studio, OpenMP, Thread Building Blocks, a whole range. A developer needs to look at these and figure out which is the best one for the type of job that he's doing and make use of them. The compiler also helps. The compiler, especially the Intel compiler, has been designed to actually use the new features of the hardware as it comes out. So it's always useful to actually look at the actual current software that's available and check. Use the right tools for the job. There's a whole range of tools out there. There's tools from Microsoft, even the graphics tools themselves for profiling normal D3D. They'll all tell you something about what's going on in the system and where the actual driver. In most games, the driver is the single biggest thing you'll face when you're actually looking at what's taking your time. Knowing how that is running makes a big difference.